Hello, ladies and gentlemen, and welcome to a very exciting new episode of Dave Does Math from Home. We are experimenting with new recording techniques. The camera's kind of not cutting it anymore, which is why this video is a little late. Let's not worry about it. This is me trying to record directly on the computer. Hopefully this is much nicer. If it's not, let me know and we'll fix it. We'll come up with a better plan if this is not a good plan. But we're going to try it out. The plan for today is to talk about path independence, and that probably doesn't mean much to you right now, but it will by the time we're finished with this. This is section 17.3, and the short version of what we're doing in section 17.3 is now that we know how to do line integrals from section 17.2, the new plan is we want to shortcut the line integral process. Line integrals can be done, as we know, in 5 easy steps or your money back guaranteed. But what if we could do it in slightly fewer, slightly easier steps? That's the goal. And it doesn't always work. This is a shortcut that works on certain kinds of vector fields that have certain properties that make doing line integrals much, much easier. And one of the names for that property is path independence. It's also called a conservative vector field. I prefer the term path independent vector field. So in this section, we're going to learn how to determine whether or not a vector field is path independent, what it means to be path independent, and then we're going to learn about the shortcut for doing line integrals on vector fields that are in fact path independent. So that's the plan for today, and I'm going to grab my notes. Okay, got my notes, got the camera rolling. Let's do this. Hopefully it should surprise no one that path independence means it doesn't matter what path you take through the vector field. At the end of section 17.2, we had this really interesting, what I think was a really interesting, really compelling math problem where we had a rotational vector field doing this sort of thing. We had a rotational vector field like this. Welcome home. And the question in the homework was asking us to do this rotational vector field in 3 different ways. In each of these problems, we started at the point 1, 0, and we ended at the point 0, 1. But the homework question was asking us to do this problem 3 different ways. First, they wanted us to do the quarter circle, then they wanted us to do the straight line, and then they wanted us to do the straight horizontal followed by the straight vertical, to see if the path that you took from here to here changed the outcome of the line integral. And we found that it did change that outcome. One of these answers was, I think, 1. One of the answers was pi. One of the answers was 0. So the path that you took from here to here had a huge impact on the result of the line integral, the work done by this force field on this path. So this is an example of a vector field that is not path independent. This vector field is path dependent. The result of the line integral does depend on the path that you take. But there are other kinds of vector fields. There are vector fields where we could do this and we would find that the result actually doesn't change at all depending on your path. So this vector field here, this was f equals negative y comma x. This was the rotational vector field. This is what I call the explosion vector field. So this is just x comma y. That's this vector field. If we do line integrals in this vector field, if we're going, let's do the same three. Those are pretty nice, easy three. If we do these three line integrals, one of them going in a circle, one of them going in a straight line, and one of them going straight back and then straight up. I want to do these three line integrals real quick to see if we get different answers each time. And hopefully, if I've planned this correctly, I think this vector field is path independent, and I think we'll get the exact same answer each time. So let me do, this is 1, 0, and this is 0, 1. Okay. Let me get my eraser, and then we can start working on this. Let's start with a circle. If we're doing a circle, the path is cosine t sine t, and then dr would be sine t negative cosine t, and f is, if f of x is xy and we need to express this, x here would be cosine t sine t. Yeah, because this is x, that's why, yes. And then f dot dr would be cosine t sine t minus sine t cosine t, which is 0. So if I integrate this, I will get 0. The amount of work that the explosion vector field does on the circle is 0 work, which sort of makes sense because this like explosion always pointing radially outward, this vector field is always perpendicular to this curve, so we should expect the dot products to always be 0. So that is the circle. Let's do it again with the straight line. Let's see what we get there. The straight line is r equals, how do we do these straight lines again? We start at the coordinates for this one. So we start at 1, 0, and we add the difference to get to here. So we need to subtract t from this and add 1t to that. So dr should be negative 1, 1. And then f should be 1 minus t, t. And then f dot dr should be negative 1 minus t plus t. Oh, and this is going from 0 to 1. So this is giving me t, 2t minus 1. So the integral of f dot dr is the integral from 0 to 1 of 2t minus 1 dt, which is t squared minus t from 0 to 1, which is 0. So that's good news. I was worried there for a second when when this wasn't 0. I was like, oh no, it's supposed to be 0. It is 0. Okay, we did do this right so far. My assertion again is that this is path independent, so we should get the same result no matter what. And so far, for the curved circle bit, we got 0. For the straight line bit, we got 0. For this horizontal followed by vertical, I think I can pretty confidently assert that that's also going to be 0 without really doing the line integral, because it's sort of symmetric. Here you have a straight line along the axis. So this is going to give you a very negative result. And this will give you a very positive result that has the exact same magnitude. Because this is going against the axis, and then it's with the axis. It's going to be encountering the exact same vectors here as it is here. It's just going to be a negative version and a positive version of the same number. So I will, in the interest of time, I will assert that that is also going to work out to be 0. And I can pretty confidently assert now that this vector field is path independent. And that's not really just a quirk of these 2 points that I chose. This really is, you could choose any 2 points on this entire vector field and do the line integral in any path you want between those 2 points, and you will get the same result no matter what the path is. So the circle, the straight line, the horizontal, vertical, all of these things are pretty straightforward, but the power of this path independence is that you could take a point here and wiggle it around and do some loop-de-loops and then arrive here, and you would still get the same answer. The path is completely irrelevant. The only thing that matters to doing the line integral on this vector field from this point to this point is where you start and where you end. So this is a very powerful result. And if we have a technique for determining when vector fields are going to be path independent, that has the potential to save us a lot of time, especially if we have weird, squirrely looping paths. Parameterizing this is not something that I or anyone else on the planet is excited about doing. But if we can skip the part where we parameterize the path and all we care about is the start and the end, that's going to be a very powerful result for us. So it's time to talk about how to tell when a vector field is path independent. And for that, I'm going to erase all the stuff that we have here. Okay, here's the good news. A vector field is path independent. No, that's not how I started that sentence. Wow. This marker is pretty excitable. Let's get, okay. A vector field is path independent if it can be expressed as the gradient of a potential function. Which is really, really nice for us, because we know about gradients, we know how to take gradients, we know how to work with gradients, and this is the secret. If a vector field is the gradient of something, then it's guaranteed path independent. If it's not the gradient of something, then it's not path independent. So if we go back to our last 2 vector fields, we had the explosion vector field and we had the rotational vector field. this, hopefully we can pretty easily imagine a potential function f phi equals xy. No, not xy. That's not the potential function. Let's do phi equals, we want the derivative here to be just x, so like 1/2 x squared. We want the derivative on this other end to be 1/2 y squared. So if this is phi, I guess plus c, some arbitrary constant here, that's fine. If we take a derivative of this potential function, the derivative with respect to x of this is 0, of this is 0. The derivative of this with respect to x is x. So that's good, that's what we want. If we take the derivative of this potential function with respect to y, we get 0, y, and 0, and that's what we want there. So this explosion vector field can be written as the potential function of 1/2 x squared plus 1/2 y squared plus c. Which sort of makes sense because we remember that gradients are vector fields that always point in the direction of steepest ascent along that surface. And so if the surface is a big like paraboloid that's just always going up, the direction of steepest ascent is always directly outward from the origin, which is why we get this sort of explosion vector field from the paraboloid surface. So we have a potential function. Its gradient is f. The gradient of the potential function is f. That's great, we did it. That confirms for us that this is path independent all the time. If we try to sort of construct a potential function for this vector field, I think we're going to have trouble. If the derivative with respect to x is negative y, that means that there needs to be a part of this function that is negative xy. This way, if we take the derivative of this with respect to x, we get the negative y, and then we're all set. In order for the derivative with respect to y to be x, we would need a piece that's just xy. Hopefully you can see where this is about to go wrong. If you simplify this, they cancel, and also introducing another piece that has x's and y's is going to change the derivative of the function with respect to x. Like we wanted this piece to be there because when you take the derivative of this with respect to x, this is correct and complete. If we add another piece here with x's in it, it's going to change the derivative with respect to x. So there's no way that we can make a potential function that has this as its gradient. That's just not ever going to work. There's some good news about easier ways to test this. This sort of test that we have done here is, can we create the potential function? And here we can create the potential function. Here we can't create the potential function. There's a way to do this that is easier than just straight up creating these functions out of nothing. So we're going to talk about that, but we're going to do it in the next video. Stay tuned.